Uh, my name is Takanori from Kobe Steel. Today, I'll be presented according to the following outline. Let me start by explaining the background. In welded structure, it is important to suppress fatigue failures in steel weld. Fatigue process of metals is mainly divided into crack initiation and crack propagation. There are various studies on the two processes, but here we focus on the crack initiation process. Our research group has found that the fatigue damage until crack initiation is delayed by strengthening the pellitic matrix through solid solution strengthening. Utilizing these research findings, 490 megapascal class steel plates were developed. This figure compares the fatigue life of conventional steel and the developed steel. The crack initiation life of developed steel is extended, so it leads to an improvement in overall fatigue life. Here is a schematic diagrams of single pass fillet weld. Heat affected zone HAZ is formed around the weld metal. The fatigue crack typically initiate either in the weld metal or HAZ. In this study, we focus specifically on crack initiation from the HAZ. The HAZ experience a microstructural change from pellitic matrix to a benitic or martensitic matrix due to welding heat. When developed steel are used for the joint, it's uncertain whether the fatigue improvement effect will also work in HAZ microstructure. Since HAZ exists locally, so it's difficult to extract fatigue test specimen from the joint. To evaluate fatigue strength to the HAZ, we created an equivalent structure to HAZ using simulated heat cycle test and obtained the smooth fatigue test specimen like this. To investigate fatigue strength in HAZ, we took two steps. Step one, the fatigue strength of the HAZ was examined using simulated HAZ specimen. For the next step, the fatigue improvement effect was confirmed by using fatigue test of cruciform fillet welded joints. I'll explain step one. This is a experimental procedure. We prepared the 490 megapascal class steel plates, conventional steel and developed steel. This table is a chemical composition of both steels. In developed steel, solid solution strengthening elements are optimally added. We conducted a simulated heat cycle test. The tests were carried out under 4 different conditions, A, B, C, D, to change the grain size and the area fraction of MA hard phase. MA hard phase is a martensite austenite constituent dispersed in benitic matrix. Then we made a smooth fatigue test specimens like this shape and tested them under cyclic axial loading conditions. And then we conducted measurement of grain size and area fraction of MA hard phase and Pickard hardness test. I'll show you fatigue properties using simulated HAZ specimens. This figure shows the relationship stress amplitude and the number of cycles. You can see that fatigue limit of the developed steel is superior to that of the conventional steel. In general, it is known that fatigue strength is proportional to the strength. So the relationship between fatigue strength and the Pickard hardness was investigated. In this study, the strength corresponding to 1 million cycles is defined as fatigue strength. This figure shows the relationship fatigue strength and the because hardness. The fatigue strength relative to the hardness of the developed steel is higher than that of the conventional steel. Moreover, the difference in fatigue strength between two steels can't be explained by because hardness. We investigate the effect of microstructure on fatigue properties. This image is a conventional, the specimen of conventional steel after heat treatment. It's identified as a Benedict matrix. These figures the relationship fatigue strength normalized by because hardness and the average grain size in Benedict matrix, as well as the area fraction of MA. The influence of change in grain size and the MA due to thermal effect on fatigue properties is negligible. Therefore, fatigue improvement effect observed in the pellitic matrix solution strengthening is also effective in the HAZ microstructure. So step 2, I'll explain the step 2. The cruciform joints were fillet welded using gas-sealed arc welding method on 12 millimeter thick plates. To induce the fatigue crack in the HAZ, grinding was performed at all weld toe. The curvature radius of a grinder bar chip is 3 millimeter. Then we conducted the fatigue test under cyclic axial loading conditions. This image is a specimen of after fatigue test. You can see that the fatigue crack were initiated from the HAZ, and the fatigue failure occurred at the ground area. This figure shows the relationship stress range and the number of cycles. This reveals that the fatigue characteristics of the weld joint were improved using the developed steel. This result indicates that the fatigue strength of the weld joints of developed steel increased where fractures occur in the HAZ. Our results are summarized as follows. Step 1, the fatigue strength of the developed steel in the HAZ was found to be superior to that of the conventional steel, as demonstrated by fatigue test using smooth specimens. The superior fatigue strength of the developed steel was suggested to be attributed not to factors such as hardness or grain size, but to the effect of solid solution strengthening in the HAZ microstructure. Step 2, it was found that when fatigue crack originates from the HAZ, there is potential for improvement in fatigue characteristics. In the next presentation, we report the findings of study focusing on the steel bridge joints, where fatigue crack occur as the HAZ. Thank you for your attention.